All right, so can you guys see it now? All right, so the premise of the lecture is, I don't know. Cool, awesome.
This is the Earth at a time when the dinosaurs roamed a lush and fertile planet. A piece trickled into the atmosphere. A trillion tons of dirt and rock hurtled into the atmosphere, creating a suffocating.
This shock wave travels about 1,000 miles per hour. Well, it's traveling that fast, it just pushes the air out of the way. And then it creates a vacuum. So that's how the dinosaurs, in essence, became extinct. Give and take. All right. So the question is this: what is the original form of energy that turns into the fireball, that creates a shock wave and causes all that destruction? All right. So you guys are thinking, oh, that's the original form is the kinetic energy of the asteroid, but that information is not 100% correct. So that's what last week we were talking about conservation of total mechanical energy. Now, total mechanical energy is a very limited scope. All right, using the conservation of total mechanical energy, you cannot explain how an incoming asteroid can cause that much destruction. All right, and because the total mechanical energy, though it's a really powerful tool, it's not a generalized case. It's a very special case of reality. And and that sort of stuff works fine if you're dealing with conservative forces, like gravity is. Okay, so you do work against gravity. Let's say he's being lifted up. She's lifting him up. And then she's doing work on this guy by lifting him up. The amount of work done on him, the amount of work that she does on him, becomes transferred to him in the form of that person's potential energy. So the transferred energy becomes the stored energy, and then she lets go. Now he's got stored energy, the potential energy. Gravity takes over. So what does gravity do? Gravity is going to turn that potential energy into kinetic, and just before impact, all the energies that he's got is in the form of kinetic energy. So the question is, what happens to that kinetic energy upon impact? Where did the mechanical energy go? All right, so this lecture is going to address that question. Conservation of mechanical energy is a useful tool, obviously, if you're ignoring the effects of surface friction, if you're ignoring the effects of air friction, surface friction. And then what happens? Now you can explain why this ball keeps going back up to the same height. Because Galileo said, ignoring the surface friction, the ball is going to keep going back up to the same height. So the question is why? The answer to that question is because if gravity is the only force acting on a system, what's going to happen, guys? Gravity is a conservative force. So initially, this thing got potential energy. Now potential energy is going to turn into kinetic energy. And so potential energy turns into kinetic energy, and kinetic energy turns back into potential energy. That's it. All right, so this is what gravity does because gravity is a conservative force. And a conservative force is what conserves mechanical energy. All right, so what conserves mechanical energy means that the mechanical energy remains constant. So the conservation of mechanical energy means the constancy of mechanical energy. So the mechanical energy is going to remain constant. Real life is not
his favorite
that simple usually.
Part of the job is testing the products. He doesn't pedal. He uses his upper body to pump himself up to 35 miles per hour, the speed he needs to get airborne.
It's great. Like when you look down on the ramps like that, you focus on the coping, which is that bar right on top. And once you stop focusing on that coping, you just see the whole ramp and the whole surroundings and stuff. So it just gives you such an awesome perspective. You just feel like you're just hanging up in the middle of the sky.
His favorite part of the job.
All right, so you have a propulsive force. It's exactly the same setup. All right, so the motion is going to start exactly at the same point, except notice that he ends up getting mechanical energy, right? So here's the initial mechanical energy, and now what happens is he ends up getting mechanical energy right there. His final mechanical energy is larger than his initial mechanical energy, so which means that he ends up getting mechanical energy. So you gain mechanical energy when there's a propulsive force acting on a system. So propulsive force generates the mechanical energy. So the question is, where did this extra energy come from? Energy cannot be created or destroyed, so you have to get energy from somewhere. So the question is, where do you get it from? All right, so in his case, this guy is using his muscles, so propulsive force is coming from the muscles. Muscles obviously utilize energy which is stored within the body. The energy stored within the body is the energy that you get from your food, so that's the chemical potential energy. All right, so depending upon what it is that you're eating, obviously you can eat meat, or you can eat plant life. So The next question is, where does the plant life get its energy from? So the plant life is going to get energy from light from the sun. All right. Also, we get a tremendous amount of heat from the sun. Light and heat is what drives life here on Earth. All right. So where does the sun get its energy from? It gets it from a nuclear fusion process. Hydrogen is what fuses into helium. Along the way, you generate a tremendous amount of heat, light, and other processes along the way. So this little bit of mechanical energy that you gain happens because of the conversion process. You're not creating energy. The energy simply is getting converted from one of these forms into the mechanical energy. And that's what a propulsive force does. Propulsive force actually converts energy from these forms into the mechanical energy. Another thing that you notice is the mechanical energy is no longer conserved when there's a propulsive force is active, which means that it's not constant. So, which means that the propulsive force is a non-conservative force. So what happens when there's friction present? Like Galileo said, ignoring friction, the ball is going to go back up to the same height. If you're not ignoring friction, the ball is not going to go back up to the same height. In fact, it's going to fall short. All right, so here's your initial mechanical energy. Here's your final mechanical energy. Notice that you end up losing this much mechanical energy. So some of the mechanical energy is lost. So final mechanical energy is going to be smaller than the initial one. So you end up losing mechanical energy. So the question is, where did the energy go? Where did the energy go, if that's the case? Remember, you cannot destroy energy. So something has to happen to energy. So where does it go? Number one, when you do this demonstration, you will hear a sound. Sound is a form of energy. If you measure the surface temperature is going to go up, which means that the heat is going to be generated. So that's part of the energy. On top of that, if there's too much friction, surface will start to glow. They're going to heat up and they're going to start to glow. So you end up getting fire out of them. All right, so once again, that's the type of energy. So what do we know? Gravity is a conservative force. All right, so which means the mechanical energy remains constant. Propulsive force is not a conservative force. It's a non-conservative force because mechanical energy is gained. Frictional force is a non-conservative force because the mechanical energy is lost. So when there's propulsion present, mechanical energy is no longer conserved. Mechanical energy is gained. When friction is present, mechanical energy is still no longer conserved, which means that the frictional force is a non-conservative force because the mechanical energy is lost. All right, but the total energy is still conserved. Total energy is still conserved. So energy can be converted from one form to another, but energy can never be created or destroyed. Now, the conservation of energy is an extremely powerful tool. Being used in all sciences and all engineering disciplines. All right, this is one of the most powerful tools, theoretical tools that we have at our disposal. All right, question number 12. This is one of the points that you really, really have to practice. Okay, and when I say practice, I mean practice, guys. I don't want to get to sort of stuff that I'm getting from you guys. Some of the work that you guys are turning in recently is kind of unacceptable. Okay, here's what I'm talking about. All right, so this is an accident scene investigation. Okay, so let me show you what I'm doing and how I'm doing it, and let me tell you what it is that I'm expecting from you guys and I'm not getting, so that we are all on the same page. You guys are engineering students. Hopefully there's 1 or 2 physics students. And the way you guys are doing work recently is just not cutting mustard at this point. All right. It's an accident scene investigation, guys. Physics deals with reality. All right. Though we use mathematics, we are still dealing with reality. Make sure that the reality that you're dealing with is front and center. I'm not seeing that in your solutions. Your solutions look too much like a math problem. And I can't even get to the physics of it. That's just so annoying at some point because you guys are just grabbing formulas, throwing things together. You're looking at my notes, and the physics is just pushed to the background. I can't even get to the physics of what you guys are trying to do. There's an accident scene investigation. What do we have? Skid marks. That's it. You got nothing else but skid marks. And the only thing you need to know is how fast was the driver going at the time he locked up the brakes. Okay, that's the only relevant information. Was this guy speeding? All right, so that's what they usually try to do. Coefficient of friction, it's a rainy day, evidently. You used to look it up. It's getting 0.42. So you have to set up the problem. Force diagrams. Force diagrams, force diagrams, force diagrams. Accurately drawn force diagrams. If you don't have a force diagram, you don't have a chance to justify your solution. Normally, if there's nothing there, if there's math, if I gotta tell you, if this was in-person education, I would give you 1 or maybe half a point, okay, out of 10 points. I don't care what you do the rest of it. I don't care about memorized work. You have to show work. Everything comes out of these little schematics that I'm drawing on the side. What do we have? The vehicle is skidding in the forward direction. It's gonna come to a stop at some point. Guess what? Because there's a frictional force acting on it. All right, so there's one force that I placed on it. So I got my schematic. This guy's gonna have an initial speed. That's it. I want to know what that initial speed is because his final speed is gonna be 0. Only information that we got is measured skid marks, and then information that you look up for the coefficient of friction, kinetic friction. So how fast is he going? What's he going? Whatever. So I've done the conversions. So far, so good. All right. So everything else is that I'm gonna do. I'm gonna involve the schematics. First thing I need to do is how do you approach a problem like this? How do you approach a problem like that? Believe it or not, 90% of the work in physics, and I'm not exaggerating, 90% of the work, the most difficult portion of physics is to figure out which formula to pick. And what helps you do that is your conceptual understanding of it. We don't just, the way we were doing it the first couple of weeks is not the way to do this stuff. The first couple of weeks, I want you guys to get used to the formulas. Right now, we passed that state. All right, right now, everything it depends on your understanding of it. Okay, which formula am I using and why? Okay, when you put down a formula on the test, you need to tell me why you're picking that formula. You can't just say, hey, these are given and this is the simple. Nope, this is not a math course. I'm not interested in that reasoning. Tell me why you're picking the formula. I will pick this formula. Let me tell you why I'm going to pick this formula. Because there's a force acting on the system, and this system is being displaced in the forward direction. There's work being done on this system. Right? There's work being done on the system. Force is opposing motion. The work being done on the system is going to be negative work, which means that the system is losing energy. The car is losing energy. This formula has everything that I need in it. Number one, the work is being done on this car because there's force opposing motion. And the amount of work that you do is the same as the amount of energy that gets transferred to the system. All right, the work is a process of transferring energy. Energy is either going to be transferred in or out of a system, and then the transferred energy is going to either go in or come out of the motion of the system. That's what it means. So it's going to go in or out of this motion itself. So you end up doing work, so work being done on the system. But the amount of work done on the system, the energy is going to change, and the energy is going to change in the form of kinetic energy. How do I know that? Because we were dealing with motion, guys. That's it. All right, immediately, I know what I'm dealing with, and then I say, okay, so these are the equations that I can use. For kinetic energy, obviously, this is the equation that we will get to use. It's the starting point. Boom. So the work done is going to change the kinetic energy of the system. So you got the final speed, you got the initial speed. So the final speed is going to be 0. So that term drops out. And once you pick the right equation, obviously now you have to, what I'm going after is the initial speed. So I'm going to keep doing the algebra until I isolate the initial speed. Now you put it on the math track. Okay, I usually call it algebra. It could be calculus, it could be differential equations. I don't care what kind of math it is. At that point, you have to follow the rules of math. Okay, that's a different department. I assume that you guys kind of know how to do your math at this point. Picking out the first formula is essential. You have to justify that. All right, so you don't need to explain it. Now I'm going to divide it by 2. Now I'm going to divide by m. I can see that. I'm not interested in that sort of information. You need to justify the first formula and make sure that you got the proper schematic to justify things. Then we go along. Obviously, you just isolate your VO and then stop at this point. Okay, so I was able to isolate the unknown. Then I take a look at the right-hand side of the equation, check to see if I got everything that I need, because I'm going to stop at some point. So the question is, one, W represents work. We're not given work. That information is not available. In real life, you don't get that sort of stuff. Work is an abstract object. On top of that, I have no idea what the mass of the car is. So which means that we're not done. Okay, so which means that I have to generate something for work. At that point, you have to go to the definition of work. You get the definition of work from here, guys. It's a combination of force and displacement times the cosine of the angle in between that you're looking at. All right, so the angle between the applied force, so the motion is in the forward direction. Instead of using r, we are using x. Applied force is going to be to the left. So the angle is going to be 180 degrees, so it's going to give us negative. All right, so which means that you end up being negative of this, and displacement is in the forward direction, or the way I do it, because these are vectors. This is in the forward direction, this is in the backward direction. So this is negative, this is positive, so it's going to give you negative work. All right, so next step is do a back substitution, because we got an expression for work. Simplify negative times negative is positive. And then stop at this point. Are we done yet? Oh, we're doing better, because the only number that we can plug in right now is x. We don't have a number for the frictional force. We don't have a number for m. What does it mean? We're not done. Okay, we have to keep digging in. All right, but we do have a mathematical expression for the frictional force. We know that the friction is going to be caused by the amount of traction that you get from the surface, and it also depends on the apparent weight. Okay, so one of the things that you guys do, and this is the reason why it started to get somewhat annoying with you guys. When you guys see an N, you assume it's W. Don't make any assumptions. No one really cares for your assumptions. Just get used to it, guys. If you're getting into engineering or whatever, when you're on the math track, okay, your assumptions will be in the beginning of the setup usually. If I have assumptions, I clarify my assumptions at that point.